In this application video, I'll be going through the steps to generate a hybrid mesh for a horizontal axis wind turbine. The geometry that I'll be using is the Sandia CX100. It's a horizontal axis wind turbine rotor with a radius of 9 meters. It's got a sharp trailing edge and a cutoff tip, two features of the geometry that we'll be handling in this video. So horizontal axis wind turbines, like the CX100, generate power through lift. So therefore, efficient designs must have low drag. Now, aerodynamic drag is really created in two regions of the flow. The boundary layer region, like around the blade and the hub, as well as the wake. So being able to resolve these two regions accurately is key. So how do you go about creating a mesh that achieves this using either structured or unstructured meshing strategies? Well, using a structured meshing strategy would tend to give you a higher accuracy solution. However, creating a structured topology for a complex geometry such as this is very time intensive, whereas creating an unstructured topology for a geometry like this takes very little time, and unstructured meshing tends to provide a little bit more flexibility in terms of resolution control, like localized clustering. So actually being able to combine structured and unstructured meshing strategies into a hybrid meshing approach is really a good compromise between meshing effort and accuracy. So in this video we'll be creating prism and hex elements in important regions like the boundary layer or the wake, and then really exploit the flexibility offered by unstructured techniques to mesh everywhere else. So with that, let's get started. Alright, so here we can see the entire geometry for the CX100. So I'm just going to turn off the outer and inner block geometries for now, as we won't need them yet. Just to zoom in here, you can see the hub. I'm going to set up an average grid point spacing to be 0.025. I'm actually going to start creating some initial topology for the hub domain. So I'm just going to click connectors on database entities here. See, we've created some connectors. I'm just going to delete the connectors that I'm not really going to need for helping me to define my surface topology for the hub. So I've deleted those. I'm going to set a default dimension of 21. And I'm going to create some structured domains here at the root of the blade. So I'll select those surfaces and make sure structure is selected and click domains on database entities up in the toolbar, and you can see a couple domains haven't been created. Again, a structured domain consists of 4 edges, so I'm going to assure that opposing edges have the same number of grid points. So I'm splitting these connectors at the constant x equals 0, which is basically an x equals 0 plane, and I'm just going to redimension these 4 smaller connectors to have the same number of points, which is 6 points. I'm going to redimension these larger connectors such that they have 16 points each. And then I can go and actually properly construct these structured domains. Selecting the connectors and just click assemble domains in the toolbar. So now we have the 4 structured domains at the root of our blade. I'm going to select the spacings down here at the root and set the grid point spacing to be 0.001 or 1 e to the negative 3. This is going to be my boundary layer spacing. As you can see, we've clustered the points towards the actual hub. Now I'm going to split these domains at that x equals 0 plane. See, I've split the front and the back domain, and I'm just going to join all these structured domains on one side and all the structured domains on the other side. Again, this is for helping us to define our topology. I'm going to do the same thing with the connectors. Select those 3 connectors and just join them, and do the same thing on the other side of the hub. Okay. Now I'm going to select this connector just on one side of the hub that I joined, and I'm going to create a normal extrusion, a database constrained normal extrusion. I'm going to select the 2 boundaries of these connectors and set it to constant X so that the extrusion doesn't bleed over onto the other side of the hub. Set my initial delta S again to 1 e to the negative 3, which is our boundary layer height. Use a moderate growth rate of 1.1. Again, it's going to be database constrained, so I've selected the database constrained shape constraint, and I'm selecting the surfaces in which I want to constrain my extrusion to, and setting the domain shape. And I'm going to turn down the volume smoothing such that we can kind of force it to maintain that initial front shape as it extrudes outward, and we're going to run it for 25 steps. Okay, so I'm going to select this domain, and I'm just going to copy it and paste it and mirror it on the other side of that x equals 0 plane. Now that I've done this, the first thing I'm going to do is I'm going to go to grid merge to check and make sure that none of my connectors were duplicated out. And you can see that they have been. There's a free edge where it shouldn't be, so I'm actually going to merge the two connectors there by picking, replace the first with the second, and apply. We've merged those connectors and we no longer have a free edge there at that intersection. I'm just going to change the display type to hidden line so it's a little bit easier to see. So now we've got these domains that we're going to help construct a collar block later on in the video. So I'm going to split these connectors that were created earlier at the extent of that extrusion and just delete the small connectors that are left over. Flip it around to the back. Do the same thing again. Select this connector and split it at the extent of that extrusion and just delete the small piece that's left over. And now I've got the boundaries that are defining the unstructured domains that I'm going to create on the hub. I'm going to just change my unstructured boundary decay default value to 0.95 for the block and the volume. This is going to allow for a much smoother transition between cell sizes in my unstructured domains. Okay, I'm going to flip to unstructured up in the toolbar and select the boundaries of the unstructured domains that I'm going to create here on the hub. So we're leveraging this hybrid approach so we don't have to spend the time defining a structured topology in a region such as this. Okay, look at the back, select the connectors on the back side of the hub. Alright, so we've created these unstructured domains, but you can see they're not constrained to the database, but that's okay. I can just select the unstructured domains and go to project in the toolbar, just uncheck interior only because we want to project all points, and you can see now 100% of the points in these domains are database constrained, and they now follow the curve of the hub geometry. Let's change the display type to hidden line. You can see now we have our hybrid surface mesh for the hub and the root of the blade. Okay. Next thing I'm going to do is I'm going to activate and set the current layer to the blade layer to create the surface mesh for the blade. I'm going to zoom out here a little bit and select the surfaces of the blade using an inclusive selection. And I'm just going to go and deselect the tip because I'm going to create, that's going to be an unstructured domain we'll create later. Just select the last two surfaces down at the root and switch to structured, and I'm going to create some unstructured or structured domains, on the surfaces of the blade. Just change the display type to hidden line. Okay. Now, again, creating these domains is an automated approach, but sometimes it doesn't create them quite perfectly. Like in this region where we already had connectors defined, you can see that there's a connector running across two connectors that we had before. So I've just deleted those domains by removing those connectors, and I'm redefining those two structured domains, recreating them. This is the benefit of Pointwise. I mean, you get the automation that you need, but also you can interrupt that process and manually construct things if you need to. So select those domains, just change them to hidden line. Alright, so I'm going to join some domains on the pressure and suction sides of the blade again, but I'm gonna leave a break at the kink because that's that's a hard break in the geometry. We don't want to join a domain across that, so I'm just selecting the domains on one side of the blade, joining them together, rotate the blade around, do the same thing on the other side. So now just selecting these domains on the suction side of the blade. And joining them together. Okay, I'm going to do the same thing with the connectors. We're just going to reduce the number of connectors, join them. We'll have a connector running along the leading edge and one running along the sharp trailing edge of the blade. Select these connectors and join them. Same down here at that hard break, we want a connector running across this to define that break in the geometry. Okay, so now that's done, I'm going to select all the connectors and I'm going to change their distribution type, which is most likely a general type distribution. I'm going to change it to a hyperbolic tangent distribution with equal spacing, and now I can actually go and start adjusting the spacings on the blade to make for a much smoother mesh. So here at the kink, I'm going to select these spacings. At the kink, I'm going to set the delta S to be 0.05. I'm going to select these spacings down here at the root, as well as here at the trailing edge. Change that space to be 0.025. And then I'm going to select the spacing at the leading edge. I'm going to cluster some points near the leading edge to resolve that curvature in the geometry, as well as cluster the decrease the spacing here at the tip of the blade, 0.01. Okay, so now we have our surface mesh for our CX100 rotor. It's a hybrid mesh. So next I'm going to go back to the hub and make it the current layer. We're going to begin constructing the boundary layer. So the first thing I'm going to do is create this collar block. So I'm going to select this ring of connectors. I'm going to do a normal extrusion, so create, extrude, normal. I'm going to do an assemble special. Rather than having one edge, we're going to do one edge per connector to maintain that topology. In the attributes panel, we'll just set the initial delta S again to 1e to the negative 3 and run it for 25 steps. Okay. Now I'm going to create a couple connectors, but these connectors are going to have the same attribute. So I'm going to set up some connector defaults, mainly a begin delta S of 0.001, 1e to the negative 3, and create this connector here at the front. And use my saved views to quickly get around to the back and create a connector here on the back. Now I'm going to construct these structured domains. So I'll select these connectors and just click assemble up in the toolbar. Do the same thing on the front, select these connectors and assemble. Okay, I've got two more domains to create, so I'm going to select the 4 edges of these domains. And same on the other side. Okay, so now we have the domains defining this collar block region, so I'm just going to use an inclusive selection and select these domains and just click assemble blocks up in the toolbar, and it's going to create 2 structured blocks. Now I'm going to split them 13 points up from the hub, so I have a basis for my prism extrusion that I'm going to do off those unstructured domains on the hub. So I'm just going to select split. I'm going to split it K direction 13 points up from the hub. Do the same thing with the other block. I'm going to just unset that so I don't forget. Alright, so now I'm going to select these unstructured surface domains on the hub and create extrude normal, do a normal prism extrusion. I'm going to set up the boundary conditions, but before that I'm going to turn on that inner block layer that has some geometry. I'm going to need to set some boundary conditions. I'm going to do some database constrained boundary conditions. So I'm going to select these boundary conditions, change it to database constrained, and begin to select the surfaces that were in that inner block layer. Set the boundary condition, do the same thing on the opposing side, select those boundary conditions, database constrained, and then select the surface which I want to constrain them to. Those inner boundary conditions are going to be adjacent grid boundary conditions, and those domains were created when we split those blocks, so we'll select those and set the boundary condition. Attributes, again, the initial delta S will be 1e to the negative 3, and I'm going to run it a total of 12 steps. So it'll match that collar block that we had split 13 points up from the hub. So you can see that the front of this extrusion is a little crinkly. Again, it's because it was extruded from an unstructured surface mesh. Using a different approach may be a little bit more difficult, and this is kind of the benefit of using a hybrid topology. Okay. So I activated the blade layer, so now I'm going to create the boundary layer for the blade. Do a normal extrusion. Again, I'm going to assemble special, delete all the faces, and I'm just going to assemble one face per domain. Go to the boundary conditions tab. So up at the tip, I'm going to select those boundary conditions, and I'm going to say I'm going to do a constant Z. Down at the root, I'm going to select those and do again, and it very similar to before, an adjacent grid boundary condition. I'm going to select that those domains that I extruded away from that ring of connectors as my adjacent grid. Set my attributes such that my initial delta is the same, 1e to the negative 3, growth rate of 1.1, and again I'm going to drop my volume smoothing to 0.01 to maintain kind of that initial front shape as it's extruding. And I'm going to extrude it a total of 25 steps. Okay. So now I have my boundary layer for my blade as well as my hub and in that collar region. So now I need to do the same thing at the tip. So I'm going to select those connectors, and we still haven't created a tip domain, and because this is a hybrid mesh, I'm just going to take advantage of that. I just created an unstructured domain on the tip. I'm going to select these domains here on the tip, and I'm just going to do a translational extrusion. So go to extrude, translate, one face per domain. It's good. Okay, we'll use the z-axis, and I'm going to extrude it a distance of 0.2. And I'm going to make it kind of fun. I'm going to use 20 steps here and run it. Okay, so now we have the boundary layer grid for our CX100 rotor. Alright, so I'm going to create a wake block now. So I've turned on empty layers. I'm creating a wake layer. I'm going to activate it and set it as the current layer. Turn on that inner block geometry. Okay, I'm going to set up a default average delta S of 0.15. Going to create a connector from the center here out to the edge. I'm going to use some transformations to adjust the size and position of this connector. So I'm going to select the connector, go Edit, Transform, Scale. I'm going to select my anchor there at the center, and my scale factor will be 0.85, 0.85, 0.85. Okay. Next, I'll go Edit, Transform, Translate. We're going to move it up from that point. Offset vector of 0, 0, 1. Now I'm going to actually split the connector at a 10% of its length. And I'm going to delete that small little connector that was created, or that was split away. Okay. So I'll just reorient the display to Y plus here, plus Y. I'm going to create a connector from that point straight up to a Z of 10. Okay. Now I'm going to actually delete the original connector. So it was just used to get the placement of that connector I just created in the right location. So I've just deleted it. Now I'm going to copy and paste and rotate this connector. I'm going to create an additional one. Rotate, point and direction. I'll select that point as kind of my pivot. Rotating about the y-axis, an angle of -60 degrees to create this nice arc. Click OK. Alright, so I'm going to create one more connector. I'm going to create a semicircular connector. I'm going to select the circle segment type, 2 points and a center, as we have all three of these points already defined here. So I'll select the 2 points and the center. We got this nice semicircular connector, and there we go. So I'm going to select these 3 connectors and translate them. Clear that translation vector. I'm going to go from this point back towards the blade, 0, 9.5, 0. And I'm just going to quickly assemble that unstructured domain up here in the toolbar. Okay. I'm going to select this inner connector, and I'm actually going to increase the number of points. So I'll go Grid, Dimension, change my average delta S value to a smaller value, 0.05. Again, now we're getting closer to the size of the cells on the blade, so we have a much nicer transition between the blade and the wake block. I'm going to select these 2 connectors. I'm going to adjust their end spacing. So I'll go Grid, Distribute, select those 2 spacing constraints, change the spacing to that 0.05 value we use for that inner connector, and I'm going to adjust the distribution function to MRQS as it's less dramatic when it comes to setting the spacings at the end. So we have a much more gradual spacing change. I'm just going to reorient here to -Z direction. Now what I'm going to do is I'm going to take this domain and go Create, Extrude, Translate. I'm going to do a translational extrusion in the Y direction, a distance of 1 and 20 steps. So now we've created a prism block. That's basically defining our wake region. Now, depending on your tip speed ratio, you may want to rotate this so it's better aligned with the blade. So I'm going to select this block and just Edit, Transform, Rotate. I'll just clear the axis there. Just going to rotate it about the Z-axis, point of the origin, 0, 0, 0, and I'm going to rotate an angle of -10 degrees. So this better aligns this wake block for the higher tip speed ratio of this CX100 rotor. Okay, so you can see we now have this nice prismatic wake block right behind the rotor. Alright, so the next step, I'm going to set the inner block as the current layer. And we're going to start creating the volume around this. I'm going to set my average delta S to 0.5. I'm going to select this kind of inlet database surface, unstructured, create an unstructured domain. Now instead of doing a transform, I'm just going to show you another way you can do it. I'm just going to cut this, paste it, translate it. Let's clear that translation vector. I'm going to translate from that center point there. I'm going to offset it 0, 5, 0. So just forward of the blade in the wake region. I'm going to copy and paste that behind, just downstream of the blade, an offset vector of 0, 10, 0. So now I'm kind of encompassing the blade in the wake region. I'm going to create an unstructured block in that region. So I'm going to create some connectors joining these domains. They're at the top here. Okay. Alright, so I'm going to select these connectors and create the rest of the unstructured domains defining the block. Created that one. Select the connectors. Okay, so now these, again, you can see they're kind of crinkly. They're not constrained to the database, so I'm going to select these two domains and project them onto the database. Just go project. You can see now 100% of the points are now on the database. Okay, so I need to create some additional connectors. So I'm going to change my average grid point spacing to be 0.1. I'm going to create a connector from the kind of the inlet region here to the extent of that prism extrusion on the hub. Do the same thing here on the back. Okay. Alright, so now I'm going to select my spacings mask, and I'm going to adjust the spacing so it matches kind of the spacing we used around that hub region. So I'm going to set the spacing to 0.025. And again, I'm going to select the spacings kind of at the inlet and the outlet regions and set that to be 0.5. Again, to better match those spacing values, have a much smoother transition in cell size. I'm going to construct the last of these unstructured domains, so I'm just going to select these domains, rotate around here, select those connectors at the extent of that extrusion, and create unstructured domain. Do the same thing on the other plane. Select those connectors. I'll rotate it around here a little bit so I can see. Pick those connectors at the extent of that extrusion. And assemble that unstructured domain. So now I've got all the domains kind of encompassing this region. Now I'm going to assemble my unstructured block. So I'll go create, assemble special block. I'm going to select the domain. I'm going to use a little trick here. I'm going to go select all adjacent, and it's going to select all adjacent domains until it can't select anymore. And if I zoom in here, you can see now we've got quite a few domains, so I'm just going to select these domains at the extent of this extrusion, as well as the extent of that boundary layer extrusion on the blade, kind of defining the first face of my unstructured block. Kind of march along the blade here. Select those tip domains. Okay, so now we've got our first face in this block, and we can select save face. You can see all the normals pointing into that block. So now I'm going to select my wake block as a second face. So I selected one of the domains. Again, I'm going to use select all adjacent to quickly select all those and just save the face. So now we have a block with an interior face. So basically we've created one block, you can see in the message window, but this is like a block object. It doesn't contain any cells yet. We need to initialize it. So I'm going to just show you, I'll just jump over the list panel here. You can see that we have this empty block. So we'll just click initialize up here on the toolbar. take a couple of minutes depending on your hardware to initialize this unstructured block. Okay, so we've taken this unstructured block object that was uninitialized. We've initialized it. You can see there's about 2.66 million cells in it now, encompassing the blade and the wake block. So I'm going to set my average grid point spacing to 0.5, and we're going to construct the rest of the blocks in this near field region, just doing path extrusion. So I'm going to create a connector from that point to the inlet. Do the same thing, just flip it around here, zoom out, create a connector that's going to act as like a path connector for this path-based extrusion to the outlet. Okay, zoom out here. I'm going to select this unstructured domain, go create extrude path. I'm going to select that connector that I just drew and use it as a path for a prism extrusion. I'm going to do the same thing downstream of that unstructured block we just created. I'm going to select that domain, go create extrude path, use that connector, and run. Okay, so now we have our near field region that consists of an unstructured block surrounding the blade and the wake, and a prism extrusion upstream and downstream. So I'm going to turn on the outer block layer. I'm going to set it as the current layer. We'll create our outer far field region. So I'll set my average grid point spacing to 2, a larger, coarser value, reduce the cell count. I'm going to select that inlet surface, a couple of these top surfaces, and the outlet surface. I'm just going to put unstructured domains on these. You can see they're purple. It's just an indication that they were created on the database. Change my average grid point spacing to 1, and just as we did before, I'm going to draw some connectors here from the inlet to that inner block. Do the same thing. I'm going to draw from the outlet. Zoom in here. You can see that point and to that inner block. And just as we had done before, I'm going to adjust the spacing. Select that spacing mask. Select those spacings and change them so they better match the spacings in that inner block region. So a value of 0.5 should accomplish that. Do the same thing here at the inlet and the outlet. Change those spacings to a value of 2. Okay, now I'm going to select these connectors and create the last 2 domains I need to construct this outer far field block. So walk around here. and click Assemble in the toolbar. Zoom in a little bit here, select these connectors, and click Assemble. Okay, so now I have all the domains defining my outer block, so I'm going to construct that block. So I'll create, assemble special block, select one of them, and I'm going to use my little tool here, select all adjacent to get all those adjacent domains. Now I'm going to come in here and select all the domains at the extent of that inner block region, and finish constructing the face of my unstructured block. Save the face. You can see all the normals are pointing into the volume that I'm currently meshing. So we've created that unstructured block object. You can see in the message window. I'm just going to select that block and click Initialize up here in the toolbar. This one has less cells. It should be relatively quick to initialize. Okay, so it's done initializing. Go over the list panel. You can see now that block 17 contains some cells. Okay, so I'm just going to go to Examine, look at the max included angle for this block. I'll just take a cut, an X cut. Let's just switch to one of my saved views here. Okay. I'll just go to the view, and we can turn off domains so it's a little bit easier to see the block there. And I'm just going to turn off this color bar so we get a little bit more screen real estate here. So you can see we've got this nice cut. So I'm just going to select all the blocks. We'll just do a cut, kind of show the hybrid nature, especially in the far field. Again, we'll go do just like an X cut. Show you can see those prism elements, the tets in the far field, kind of encompassing that inner tet block around the blade and the hub. Zoom in here, you can see the boundary layer around the blade, those hex elements. Zoom in a little further, you can start to see those prism elements off the hub itself. So with that, we hope you enjoyed our hybrid meshing application video. And if you have any questions, feel free to contact our support department. You can visit the website at pointwise.com/support.